To relate the flux picture to Newton's statement of his law of universal gravitation, and to see why the gravitation is an inverse square function in particular, we start with the hypothesis that the total gravitational flux of a mass is constant. It's equal to this, as you know, and uniformly distributed in any sphere that has the same center as the mass. In that case, the gravitational field strength, which is of course the acceleration of gravity, is just flux divided by area, which is flux over 4 pi r squared. Since the flux is constant, you divide it by 4 pi, you still have a constant. It's some constant over r squared, so that the gravitational field strength is inversely proportional to the square of the distance from the mass. The force on the mass, okay, if we have a mass m2, we can see that the force on that mass has to be m2g, which is m2 times this constant over r squared. And so we have an inverse square force. We can, of course, determine the precise gravitational acceleration by writing down the expression for the flux and obtaining this expression, which means that the force on a mass m2 would be g times m2 over r squared, and this is going to lead us directly to Newton's statement of his inverse square law of universal gravitation. The work-energy theorem says that if no work is done on or by a system, then for the system, the kinetic energy change and the potential energy change add up to 0. That is, kinetic and potential energy total doesn't change. Of course, that means that the change in kinetic energy is equal to the negative of the potential energy change. If there is a work delta W done by an isolated system, I'm not sure that the word isolated needs to be there. I don't know how you do work with an isolated system. But in any case, the change in kinetic plus a change in potential plus the work done by the system has to equal 0, which means that the change of kinetic and potential, total change of kinetic and potential energies, has to be the negative of the work done by the system. This means that work is done by the system at the expense of kinetic and potential energies. Of course, this could be written as delta W equals the negative of the total of delta KE plus delta PE. However, if the work done by the system is positive, then we can see that this side is negative. So if the system does positive work, then the kinetic and potential energy change, total change, must be negative. And that means that work is done, again, at the expense of kinetic and potential energy. Now, any of these quantities can increase, then, only at the expense of the sum of the others. Any one of these quantities can increase only if the total of the other two decreases. That might be that two of the quantities increase and the other decreases, but that still doesn't change the accounting that we have here for energy. Okay? So if one thing decreases, the sum of the others decreases.